So welcome to Unique Academy YouTube channel. So in this video, we will see gate problems from thermodynamics. So question number 1, a rigid tank of 2 meter cube internal volume. So you have a rigid tank. Of volume 2 meter cube, mass 5 kg. As a saturated liquid vapor mixture. So here you have a this total mass is mass of liquid by mass of gas. So you have mass of liquid, mass of gas. The total mass is 5 kg. The pressure is 200 kPa. At 200 kPa, sorry, 400 kPa. Pressure is 400 kPa. At 400 kPa, you have the properties. So half of the mass of the saturated liquid in the tank is trained off while maintaining constant pressure of 400 kPa in the tank. So half of the mass of saturated liquid in the tank is trained off. That means, so the mass of the tank after half of the mass is trained off, so the remaining will be this. The mass of the liquid after half of the mass of the saturated liquid is trained off is mf by 2. But mass of gas is the same. So mf is the initial mass of the saturated liquid in the tank. mg is the initial saturated vapor mass inside the rigid tank. M dash F, G dash F, sorry, M dash G, or the mass of the saturated liquid and mass of the saturated vapor after the after half of the mass of the saturated liquid is trained off. So what is the final quality of the mixture? So final quality of the mixture is X dash is mg dash by mf dash plus mg dash. This is the final quality. So this will be equal to mg dash equal to mg by mf by 2 plus mg dash equal to mg. So this you can take it mf by mg 2 plus 1. So if you know the ratio mf by mg, you can get the final quality of the mixture. So what is the initial quality of the mixture? So specific volume V by M is equal to Vf plus X into Vfg. This is your initial state. So V is 2 meter cube. The total mass is 5. Vf is given 0.001084. X is what we want. X is the initial quality of the mixture. X dash is the final quality of the mixture. Final means after removal of the saturated liquid from the rigid tank. So Vfg is given 0.46138. So now you can get to the X. Point 0.86, the Trainer's fraction. So this you can write as mg by mf plus mg. So this will be 1 by mf by mg plus 1. So this will give you mf by mg. Once you get that, you will be able to get X. Would be 0.16. So that if you substitute 1 by 0.16 divided by 2 plus 1. So this will be your final quality of the mixture. Point 0.93. So your final quality of the mixture is 0.93. So the answer is 0.93. So now we move to the next question. So in a liquid vapor phase change process, you are given dP by dt saturated at 100 degree centigrade for saturated water is, so what is given is dP by dt saturated is equal to 3750 Pascal per Kelvin. Temperature T is equal to 100 degrees centigrade, 273 Kelvin, 373 Kelvin. So specific volume change Vg minus Vf. So this is Vfg, 1.672 meter cube per kg. So what is the enthalpy of vaporization? So we know that the Clausius-Clapeyron equation dP by dt saturated HFG T into Vfg. So this is the Clausius-Clapeyron equation. Then substitute all the values, so you get HFG equal to T Vfg dP by dt saturated. Temperature 373, Vfg 1.672 This is 3750. Since it is in Pascal per Kelvin, Pascal is Newton per meter squared. So the resulting unit you will get in joule per kilogram. That is your, maybe you can convert to kilojoule per kilogram. Two, 710 joule per kilogram. 2338.71 kilojoule per kilogram. So it is right in integer 9 kilojoule per kilogram. That's the answer. We move to next question. So an office uses a heat pump to receive. So you have an office. So this is the office room. Office room. Office uses a heat pump to receive. So office is receiving the heat. And office is maintained at the temperature 300 Kelvin. This is your T1. And it receives the heat of 500 kilojoule per day. So this is the Q1. 500 kilojoule per day is 500 divided by 24 hour. 3,600. So it is something around 5.78 10 power minus 3 kilojoule per second. Okay, so let's, or this is in kilowatt. So a heat pump. So which require the work input. This is actual engine, not the Carnot engine. Work input. It takes heat Q2 from a lower temperature reservoir, which is at T2, 280 Kelvin. So COP of heat pump is 60% of its theoretical maximum value. COP of the heat pump actual is equal to 0.6 times of COP of heat pump Carnot. Because theoretical maximum value is for Carnot engine. So we know that COP of heat pump for Carnot engine Carnot is equal to T1 by T1 minus T2. So T1 is 300 by 300 minus 280. So this will be COP of Carnot is 15. Maybe you can get from this itself, you can see. So what is asked is the ratio of actual work input. So work input actual to the minimum theoretical work input. So theoretical work input is Carnot. So in the Carnot engine, the work input will be minimum compared to the actual heat pump. So maybe from this equation, you can see that this will be Q1 by work input actual. This will be 0.6 times COP of Carnot heat engine. Only work input will be changing. All the other parameters are the same. So work input is changing the COP. So this also Q1 by work input Carnot. So this you can get work input actual by work input Carnot is equal to 1 by 0.6. 1.67. Rounded up to 1 decimal places. 1.7. 1.7 is the answer for this question number 3. So now we move to question number 4. So a heat source at temperature TH, maybe I make it here. A heat source at temperature TH gives out the heat, transfers the same amount of heat to the sink under two cases, TL1, TL2. So this is the source. TH gives out heat to the sink, which is at temperature TL1. So the amount of heat, this is case A. Case B is TL2. Case A. So the source, same temperature, same amount of heat, but sink is at a different temperature, TL2. This is case B. TL1 is less than TL2. TL1 is less than TL2. TL2 is greater. So there are 4 statements. Reversibility is same. Entropy generation is greater than 0 for both case A and B. Reversibility is less. Reversibility is more. So we need to find out the reversibility of the cases A and B. So how do you find out reversibility? So we can find the entropy change of the universe. So maybe we can take this as a universe. Universe A. This as universe B. So the entropy change of the universe is more. More is the irreversibility. Less is the reversibility. More is the irreversibility. Less is the reversibility. Okay, so now we need to find out entropy change of the universe for A and B. Let us calculate that. First, entropy change of the universe A equal to, it has two, source and sink. 1, 2. So entropy change of source, entropy change of sink. Source is losing heat, so it loses entropy, so minus Q by TH. Sink is gaining entropy, so plus Q by TL1. This will be definitely positive because your TH is more than TL1. TH is more than TL1. So entropy change of the universe will never be less than 0. It will be always greater than 0. So it is greater than 0 because of irreversibility. Irreversibility generate entropy. Okay, so it is greater than 0. Now come to this entropy change of universe B. Again, this is the source 1, sink 2. Entropy change of source, entropy change of sink. Source losing entropy, so Q by TH. Okay, so whenever you have a source or sink, the temperature is constant, the entropy change will be Q by T. Okay, otherwise, integral dQ by T. If the temperature is changing, then you have to calculate using dQ by T. So this sink is gaining entropy because of the heat it gains. Again, here it is the same. TH is greater than TL2. So entropy change of the universe P is greater than 0. Now comparing these two, A and B. So this part is same for both. Entropy change of this part is same for both. But if you look at that, the other part, Q by TL1, we know that TL1 is less. So this will be more than Q by TL2. So your entropy change of universe A is more than entropy change of universe B. This indicates that case A is more irreversible because entropy of the universe is more irreversibility than case B. But there it is talk about reversibility. That means case B is more reversible. A is more irreversible. That means B is more reversible. B is more reversible than case A. And entropy change for both A and B will be greater than 0. Case B is more reversible than case A. Case B is more reversible with entropy generation greater than 0. So C is the answer. So this will be your answer. Case B is more reversible. A is more irreversible. B is more reversible. All other answers are wrong. Okay. So now we move to the next question. The temperature of 10 gram of liquid water in an insulated container. So we have an insulated container. Insulated container. That means heat transfer will be 0. So there is some mass of water. So mass of water is 10 gram. Cp of water 4.2, it might be kilojoule per kilogram Kelvin. Sorry, kilogram per kilogram Kelvin will be equal to 4.2 joule per gram Kelvin. Both are same. Is raised by 5 Kelvin by a stirring action. So that means you have a, so by this the temperature rise delta T is 5 Kelvin. So you are raising the temperature by 5 Kelvin by a stirring. So this is the stirrer. So this will give you the work transfer into the system. So work transfer, the work is given to the system, and by that the temperature is rising. The amount of heat transferred to the water. So there is no heat is transferred to the water because the container is insulated. So since the container is insulated, there is no heat transfer. But the temperature is rising because of the work transfer. So the work transfer causing an irreversibility which increases the temperature of the water. The amount of heat transfer to the water is zero. C is the answer. So thank you for watching this video. If you are happy with this video, please subscribe the channel and share this video to your friends who are preparing for GATE Mechanical Engineering subject. If you want to join for GATE 2026 video course, please contact this number. Thank you.